Hello everyone, welcome back to the fourth lecture of the lecture series Signals and Systems. In this video, we will see about the linear time invariant systems and then what is a convolution integral. Then we'll see the properties of convolution integral and finally end with the properties of LTI system. So let's get started. So firstly, we'll see what are linear time invariant systems. Linear time invariant. This is also called as LTI systems. So in the previous lecture, we actually saw the properties of systems. So this linear and time invariant is actually the two properties of the system, right? So linearity. Linear system, what was the definition? A system satisfying the additivity and homogeneity condition, which is together called as the superposition. Right? So what is the additivity condition? So if x1 of t gives output as y1 of t, x2 of t gives output as y2 of t, then x1 of t plus x2 of t should give an output which is y1 of t plus y2 of t. And what was the homogeneity? If x1 of t gives y1 of t, then ax1 of t should give ay1 of t. And a belongs to complex number here. So a simple exercise to see that additivity does not imply homogeneity, right? Additivity not necessarily implies homogeneity. So you can take a simple example of y of t is equal to real of x of t. Okay. So in this case, if you take x1 of t and x2 of t, actually y of t will be real of x1 of t plus x2 of t. And since real parts are commutable, you can actually take this out. x1 of t plus real of x2 of t, which is nothing but y1 of t plus y2 of t. But on the other hand, if you see homogeneity, let's take a as some imaginary number. So x of t is, let's say, real. So then y1 of t equal to real of x1 of t. x1 of t is nothing but x1 of t itself. But y prime of t, which is nothing but real of jx1 of t, is actually 0 and not equal to jx of t. So this is an example that additivity not necessarily implies homogeneity. So both these conditions are necessary for that system to be linear. And together they are called as superposition principle. Okay. So this is for the linear system. What about the time invariance? Invariant system. So if the input to the system is a time shifted version of a signal, then the output signal is also time shifted by the same amount. So if x of t gives y of t, then x of t minus t naught should give y of t minus t naught. Okay, this is the time invariant property. So LTI system is a system which is both linear and time invariant. Okay, and these systems are in general useful, and we need to study them because most of the real life systems we would encounter is mostly linear and time invariant. So many systems we encounter are LTI, and also like the analysis of LTI system is much simpler and it is also elaborate. And in general, because of the superposition principle, we can actually send, study the inputs, input-output relationship of the system one by one and then finally add them, right? The input-output relation can be obtained one at a time and then finally summed up. So because of this useful property, even we try to model some of the nonlinear systems as linear systems. So now we'll study about the convolution integral and see how it is actually making the LTI systems more special. Okay, convolution integral. So first what we are going to do is, we are going to represent the signals in terms of impulses. So since I'm only talking about continuous time signals here, what idea I have is we'll just complete all the continuous time counterparts and then go to the discrete time domain. Yes, that I think will be, you will have a flow because of that. So whatever I am doing here, it is only purely continuous time signals. So representation of continuous time signals in terms of impulses. So we already saw the impulses, right? So unit impulse, which is nothing but delta of t. And how is it defined? So delta of t equal to 0 for t not equal to 0 and integral minus infinity to infinity delta of t dt. The area under the unit impulse is 1. And we also saw the shifting property. Do you remember? Shifting property. So which is nothing but integral some function delta of t minus t naught dt. So this actually we saw it is equal to x of t naught, right? So now we'll use these information to represent the continuous time signal, any continuous time signal in terms of this impulse function. Okay, so first we'll consider some continuous time function this way. So I'll copy it. So let this be called as x of t and this is the time axis. So now what we'll be doing is, we'll define some x tilde of t. or x bar hat of t. And what we are going to do is, we'll actually sample it. Let's say at 0 we sample and then hold the value. And then at, let's say, some delta we sample it and hold the value. And sample at 2 delta, hold the value. Sample at 3 delta, hold the value, and so on. So this way we sample it, and even on the negative side. So we sample it at minus delta and hold the value, and so on the negative side. So what happens? So how can I actually write x tilde of t? So before that, we'll see how we define the impulse, correct? So impulse, we actually defined it as minus delta by 2 to delta by 2. And this is 1 by delta. Let's say this is some delta with delta of t. Okay. And we actually sent delta to 0 such that it becomes a impulse. So now what we'll do is we'll slightly see a different version of this. So it is equivalent to also defining this as from 0 to delta and this as 1 by delta. And if we fit in delta to 0, still this width is actually decreasing and this height is tending to infinity. So this is also an equivalent representation. So we also saw the representation of a triangle, right? So there are many representations in which we can obtain the delta function. So this is one of the equivalent representation. Okay. So if you compare with this, you can actually each of these is nothing but like an impulse function and shifted in time. So I'll copy it. Each of the region are similar to the impulse function delta of t shifted in time and amplitude equal to the sampled value of x of t, right? So it's like x of 0, x of delta, and on the other side it is x of minus delta. The sampling at that point and holding. So shifted in time and amplitude equal to sampled value of x of t. So how do you write this as a summation? So this is nothing but x tilde of t is nothing but summation. I will take some k. So x of k delta, which is the sampled value, into delta of t. And this value should actually be 1, right? So for that, I multiply it with a constant delta. Okay, so this will be nothing but 1 from 0 to delta. Correct. And I want the shifted ones, right? So this will be minus k delta. Right, now this is shifted in time. So this will be 1 from k delta to k plus 1 delta. So only there this value will be valid. And we multiply by delta just so that we make this 1 by delta equal to 1. Okay. And where will k run from? K will actually go from minus infinity to infinity, right? So this is the representation of x tilde of t. But if you see, as I decrease the limit of delta, what will happen? So as I decrease the value of delta, what happens? You can see as a decreased value of delta, the k will actually is increasing, right? So if you take a particular region, let's say 0 to 1, and let's say delta is something like 0.5, you will have 2 units, correct? k will be 2 inside the space. In the space. Now if you take delta to 0.25, then k will become 4. But what you can observe is k delta is still remaining as 1. So k delta is remaining as constant. But delta itself is decreasing. When delta decreases, k increases. Okay? And what happens in the limit delta tends to 0? As I decrease the value of delta, k increases within any given space. And what happens to x tilde of t and x of t? It approaches closeness, right? X tilde of t is, x hat of t is approaching x of t closely, right? For example, let's say if this is x of t, I will take a big delta. Then x tilde of t will look like, x hat of t will look like this. Right? But if I take a smaller delta, as I reduce delta, small delta, how will it look like? Okay, it will look like this. Look like this. You can see it is approaching x of t. So x hat of t approaches x of t as delta is reduced. And what happens when delta tends to 0? Limit delta tends to 0, x hat of t. Right? This actually becomes x of t itself. Correct? And what happened to our right hand side here? So the summation will be replaced by an integral. Correct? So whatever we have here is nothing but, it is just like saying the area under this, right? So each of this will carry a area of 1, and that is multiplied by delta, and this delta is tending to 0, and this k delta is some constant, and this x of that constant will be the value. So it is like the area under this. So which is nothing but, I will call k delta as some tau. And delta itself tends to some integrating constant, d tau. It is very small. So my x of t will be integral from here, x of tau. And we have, so delta of t minus k delta. So what does this tend to? So k delta tends to tau. And as delta approaches 0, what does this function go to? This function goes to delta of t, the impulse function, right? So this itself goes to delta of t minus tau. So this goes to delta of t minus tau. And this delta itself goes to d tau. It is the integrating constant. And this range is from minus infinity to infinity. So you can actually go through the derivation once again, and even for your sake, you can observe why this summation is turning to an integral, right? Because like delta becomes small and the k becomes huge, and then we actually obtain the integrating constant, which is d tau, and we replace k delta with tau. So this is what we call as the convolution integral. As you can see, we have represented x of t, which is a continuous time signal, in terms of shifted impulses, right? So delta of t minus tau is nothing but impulses which are shifted in time, right? And x of tau is the value of x of t at that particular time. Okay. So how does it actually look? So delta of t minus tau, how does it look? You can see here the time axis is actually tau. right? Your integrating constant is tau. Tau is the one varying. So how does delta of t minus tau look? So at some point there is t, right? So if you have first delta of t itself, delta of tau, it will just be this one. And how will delta of t plus tau look? This is just, or tau plus t, right? First we do the time shifting operation, then we do the scaling. So how will tau plus t look like? It is just a left shift by t, right? So it will look like this, t, and then you do the reversal. So delta of tau minus t. This will not be nothing but, so left shift by t will actually bring it to minus t, and when you do the reversal it will go to plus t. And then you have x of t, something like this, x of tau. And what you are doing, you are using this impulse to sample this at each point, right? All continuously. And then what you are doing, you are just adding them, right? And each of this impulse will have value only at this one particular place. And actually adding them will give you only this line, right? So that is the convolution integral. And it is given a special symbol. So we call it x of t convolved with delta of t. So this is nothing but minus infinity to infinity x of tau delta of t minus tau d tau. So if we call some y of t something like this, then we get this. So in general, this t is just a variable, and ideally you should write it as x convolved with delta of t, because this individually they don't depend on t, right? So we have x of tau and delta of t minus tau inside, and this tau is the integrating variable and t is the variable actually associated with y of t. So y of 0 will be integral minus infinity to infinity. Here it is nothing but x of t itself, correct? We saw from the previous thing. This is nothing but x of t itself. So x of 0 will be, you can see, x of tau delta of minus tau d tau. And delta of minus tau is equivalent to delta of tau. So this will nothing but x of tau at tau equal to 0. So as you can see, this is nothing but x of 0. So this is an example. In general, convolution of two signals is defined like this. So y of t is equal to some, let's say, x convolved with h of t. It is defined as minus infinity to infinity x of tau h of t minus tau d tau. So this is the general definition of convolution of two signals. You can see it follows from this definition, right? So now with this information, we'll actually go ahead and see what special property of the LTI system does this convolution integral reveal, right? Speciality of LTI systems on this convolution integral. So what do we have? We have x of t is equal to integral minus infinity to infinity x of tau delta of t minus tau d tau. So this is valid in general for any signal, right? Now suppose I pass this signal x of t through a system, and let's say I call this as linear and time invariant, then what will be the output y of t, right? There is a special case for this LTI system. So for this, let us go back to this expression first. So this expression, okay, x tilde of t, copy, so let me say that this x tilde of t is passed through the LTI system and I get an output. So first let us take any general system, okay, and I get an output y tilde of t. And if I tend delta to 0, then this goes to x of t and this should actually go to y of t, right? So with that case, we'll actually see what happens. So if I pass this x tilde of t, it is nothing but, it is a sum of each of these signals with k value. So it is like x of 0, delta tilde of t minus 0, which is delta of t delta, plus x of 1, x of delta of t minus delta into delta, and so on. And this side also, correct? So the summation is like this. X tilde x hat of t, right? So now if I say that the system is linear, then what will be y tilde y hat of t? So like if I call it, this is x, each one is like xk of t, right? Then my y tilde of t will be nothing but summation k equal to minus infinity to infinity yk of t, right? For each of these system response. And then if you also say, so then what will I have? I will have, since this is a constant, only this is going to change. These two are constants, right? For each particular signal, xi of t, xk of t, these are constant. And only this delta term will actually undergo a system change, right? So I'll call the system response for delta of t as some h k delta of t, okay? So let s delta of t minus k delta give output h k delta of t, okay? Then what will my y hat of t be? It will be summation k equal to minus infinity to infinity. The constants will remain and only, sorry, this is k delta, and this will change k delta of t into delta, right? You can see like each term is coming here and only this is getting modulated, right? Only the signal portion, whatever is varying. The constant remains same because of the fact that it is linear, right? So a into x of t gives a into y of t. Because of the linearity, the constant term remains as it is. So I'll write it down, that also. The constant terms remain as such due to linearity. So you can now itself see that you have a very good form. Only that this hk delta of t, if somehow I am able to represent it in a different way, you will get a special form. So what I do, I use the time invariance property. So what does it say? If x of t gives y of t, then x of t minus delta or t minus tau should give y of t minus tau, right? So same way, if delta of t gives some h of t, this is delta delta, then delta delta of t minus k delta should give h delta of t minus k delta. So what it means? Hk delta of t is nothing but h delta of t minus k delta. Okay, so then what will my y hat of t be? It will be summation k equal to minus infinity to infinity x of k delta and h delta of t minus k delta into delta. So now you can see this and the x of t. So x tilde of t, this and this equation you can compare. So I'll just copy it here. So it will be easy for you to compare. So now you can see it, right? So everything looks the same. Only this delta has been replaced with h. So h delta, or we'll take the limits. So limit delta tends to 0. What will happen? X of t becomes integral minus infinity to infinity x of tau delta of t minus tau d tau. And let's say y of t becomes minus infinity to infinity x of tau. Instead of delta, you have h here. H of t minus tau d tau. And what is h of t? H of t is nothing but limit delta tends to 0 h delta of t. Here it was h delta of t. Here I have written h of t. And this is called as the unit impulse response of the system. So why it is called like that? Because we assumed here delta of t actually gives h of t. So this is nothing but the impulse, and h is nothing but the impulse response of that particular system, right? So it is called as the impulse response of the system. It is actually unit, but usually we can also ignore it and just call it as the impulse response of the system. And this is actually the convolution integral we had already defined earlier. If you see convolution of two signals. We saw it as, it is nothing but x of tau, h of t minus tau d tau. So for LTI systems with impulse response h of t, the output y of t is given by, what is it? It is just the convolution of x of t, the input signal, with the impulse response. So this is nothing but integral minus infinity to infinity x of tau h of t minus tau d tau. So it is like saying we already saw that any signal can be represented as a sum of shifted versions of the impulses. And because it is an LTI system, the output also will be the sum of shifted versions of the impulse response. Okay, we'll just see a small example of how this integral actually works. So example. So let us take two signals. I will call x of t as e power minus at u of t. And let's say a is greater than 0, so that it actually dies down to 0 when t tends to infinity. And I'll take h of t as u of t. So how do I find this integral? So first let us write these two things. We'll draw these two things and try to understand. So x of tau, how does it look like with respect to t, with respect to tau? So it is e power minus a tau u of tau. So it is 0 all the way here. It comes to 1 here and then dies down to 0. And how does h of tau look like? H of tau is nothing but u of t. This is u of t. But I want h of t minus tau. So what do? I first shift this. So tau plus t. So I shift it to the left by t, right? So I shift it to the left by t, which is nothing but I'll get somewhere here. If I shift to the left by t, this will actually be minus t. And then I take the reflection of it. So minus t. So I'll get t minus tau. So it will actually be reflection of this, which is nothing but something like this. Right? So to draw it, it will actually be something like this. So this will be t. And this value will be 1. Now I need to perform this integral. You can see tau is varying from minus infinity to infinity. But it is the value, it is the integral integrating variable. And what is this t? T is nothing but y of t. Now I want to find y of t for different variables. So find y of t. So now what I will do, I will vary this t. So vary t and then find the integral. Right? For example, if I want to find at a particular point, let's say y of 0, what I will do? I will find x of tau, h of minus tau, d tau, minus infinity to infinity. Right? So h of minus tau will actually be this integral. And you see there is no overlap as such between these two. So this will turn out to be 0 because no overlap between x and h. Right? So I will define actually 3 regions to find this. So for t less than 0. So in that case, what will this be? X of t is remaining same. X of tau remains same. What about h of t minus tau? So if t is less than 0, this will actually be on the left hand side. Right? So this will be like this. And as you can see, no overlap. No overlap. By no overlap, what do I mean? You need to multiply these both and then take their area under them. But if you multiply left hand side, you can see this is 0 and this is having some finite value. But if you multiply, everything will be 0 here. And here, the x of tau is having some value, but h of t minus tau is actually 0. So even if you multiply here, it will be 0. And then if you take area under the curve, which is just 0, it will be just 0. So what you can say is y of t is actually 0 for t less than 0. Now let us take for t greater than 0. Greater than or equal to 0. So in that case, what happens? So x of tau remains same because that is not moving with respect to t. And then I have h of tau, t minus tau. So h of t minus tau. Now t is greater than or equal to 0. So it will be something like this. And this is t. And this is tau. And what is this function actually? E power minus at, right? Only in this region. You can write it as u of t also, no issues. And this is nothing but the u of t itself. U of t minus tau, like that. So now if I integrate this, so I of t is equal to integral minus infinity to infinity, x of tau, h of t minus tau, d tau. You can see beyond t, for t greater than 0, this integral is actually 0. So I will just integrate from minus infinity to t, x of tau, h of t minus tau, d tau. But also if you see below 0, then also it is 0, right? One of the signal is 0. So it is just sufficient for me to integrate from 0 to t, x of tau, h of t minus tau, d tau. And what is the value of x of tau inside that region? Inside this region, it is e power minus at. And u of t, because we are considering from 0 to t, u of t anyway will be 1. And then h of t minus tau. So in this region, h of t minus tau is also 1. Right? And then we have d tau. This is h of tau, so it is tau here, not t. So this is equal to 0 to t e power minus a tau d tau. So now if I integrate this, what will I get? I'll get e power minus a tau by minus a from 0 to t. If I evaluate this, I'll get e power minus at minus 1 by minus a, which is nothing but 1 minus e power minus at by a. And this is y of t for t greater than or equal to 0. So what is the final value of y of t? It is 0 for t less than 0. So I can combine these both, right? You already got for t less than 0, it is 0. I can combine these both and write y of t is nothing but 1 minus e power minus at by a into u of t. So this will be the convolution integral of e power minus at u of t and u of t. So this is how you need to actually perform the convolution. So now let us see some properties of the convolution integral. So properties of the convolution integral. So the first property is the commutative property. So what it states is x of t convolved with h of t is equal to h of t convolved with x of t. Okay, so we'll try to prove this. So LHS, let's take x of t convolved with h of t. I'll write down the convolution integral here for your reference. So x convolved with h is nothing but integral minus infinity to infinity x of tau h of t minus tau d tau. Okay, so this will be nothing but integral minus infinity to infinity x of tau h of t minus tau d tau. Now let's see what about the RHS. RHS is actually h of t convolved with x of t. So here x will be replaced with h and h with x. So h of tau x of t minus tau d tau. So I need to prove these both are actually equal. So what I do is I just take this variable t minus tau and I replace it with the variable phi. Okay, so then what will happen? Minus d tau will be equal to d phi. So d tau will be equal to minus d phi and limits will be from, so tau equal to minus infinity will actually correspond to phi equal to infinity, and tau equal to infinity will correspond to phi equal to minus infinity. So RHS will be integral infinity to minus infinity. So h of tau will now become, so tau itself is nothing but t minus phi. So h of t minus phi x of phi into minus d phi. And this minus symbol I use it to invert the limits. So it will be minus infinity to infinity h of t minus phi x of phi d phi. This is nothing but minus infinity to infinity x of phi h of t minus phi d phi. Now can you see the relation between this and this? So these both are same, right? Only the integrating variable is different, but that does not matter. You can write any variable. So I'll just replace it with tau. So now this is nothing but LHS. So the convolution integral is actually commutative. So as second property, we'll see the distributive property. So what does distributive property says? x1 of t plus x2 of t convolved with h of t is equal to x1 of t convolved with h of t plus x2 of t convolved with h of t. Okay, so let us take LHS x1 of t plus x2 of t convolved with h of t. So this will be integral minus infinity to infinity x1 of tau plus x2 of tau into h of t minus tau d tau, right? Now I just expand this, so it will be minus infinity to infinity. x1 of tau h of t minus tau d tau plus integral minus infinity to infinity x2 of tau h of t minus tau d tau. So you can see these individuals are nothing but x1 of t convolved with h of t plus x2 of t convolved with h of t, and which is the right hand side. So the convolution integral is distributive. So you also need to observe one thing. Firstly, what does this write? The commutative property, what does it say? X of t convolved with h of t. This is nothing like but equivalent to passing x of t through an LTI system with impulse response h of t, right? And they are saying this is equal to h of t convolved with x of t, which is nothing but passing h of t to an LTI system with impulse response x of t. So both gives the same output, right? So passing x of t to an LTI system with impulse response h of t and passing h of t to an LTI system with impulse response h of x of t, right? So gives same output. And what about the distributive property? So h of t passing x1 of t plus x2 of t and getting an output y of t is equivalent to individually passing x1 of t and x2 of t and then adding the outputs y of t. Let's say this is y1 of t and y2 of t. This is straightforward from the linearity, right? Okay. And the third property we'll see is the associative property. So what does this property say? So it says x1 of t or x of t convolved with h of t, h1 of t, and then convolving this result with h2 of t is actually equal to x of t convolving with the result of h1 of t convolved with h2 of t. So this is the associative property. So now let's try to prove it. So left hand side, what do we have? So I have x of t convolved with h1 of t and then that is convolved with h2 of t. So first I will just elaborate this. Minus infinity to infinity x of tau h1 of tau h1 of t minus tau d tau t minus tau d tau, and this result I actually convolved with h2 of t. So I will take the second integrating variable as phi. So it will be minus infinity to infinity. This is tau. This is actually phi. Tau equal to minus infinity to infinity. X of tau, h1 of this t I have to replace it with phi. Phi minus tau d tau. And then h2 of t minus phi d phi. So you can take a minute to actually absorb this and digest this. So I have just replaced t with phi here and h2 of t I have replaced it with t minus phi and the integrating variable is phi here, and the limits are from minus infinity to infinity. So this is the LHS. So RHS, what do we have? I have x of t convolved with h1 of t convolved with h2 of t. So this is nothing but x of t convolved with, so this is minus infinity to infinity. So here I will take the variable phi just for convenience. So this will be h1 of phi, h2 of t minus phi, d phi. Now I am convolving it with t. I will take the integrating variable now as tau. So tau equal to minus infinity to infinity, x of tau, integral phi equal to minus infinity to infinity, h1 of phi, and h2 of t will be replaced with t minus tau. So t minus tau minus phi, d phi into d tau. So now I need to bring this to this form, right? So what do I do? So you can observe that tau and phi are independent, right? So with that observation, we can actually integrate either tau first and phi second, or phi first and tau second. So I'll just take a common integral. Tau equal to minus infinity to infinity, phi equal to minus infinity to infinity, x of tau, h1 of phi, h2 of t minus tau minus phi, d phi, d tau. And from the LHS, if you see, we are doing the tau integration first and then the phi second. So, but what we'll actually do is, we'll do the phi first. So, tau equal to minus infinity to infinity. So, x of tau contains only tau terms. So, that will come outside the phi integral. And then we have h1 of phi minus tau d tau into h2 of t minus phi. And this d tau is also tau integration. Let's take it here. Or let's put it in the finally. So, h2 of t minus phi d phi, correct? So this value, and whatever answer comes there, we will then integrate with that d tau, okay? So now we want to make these both equal. So you can see this differs only in terms of this variables, right? So what I will do is, I will do a change of variables. So phi prime equal to phi minus tau. So inside this phi integral, tau is like a constant, treated like a constant. So d phi prime will be d phi. And what my limits will be? My limits will actually be same, right? Phi equal to infinity implies phi prime equal to infinity. Phi equal to minus infinity implies phi prime equal to minus infinity. And what will my phi itself be? Phi itself will be phi prime plus tau, right? So then what I have on the LHS, tau equal to minus infinity to infinity, x of tau, and then integral phi prime equal to minus infinity to infinity, phi prime, h1 of, this is phi prime, and h2 of t minus phi prime minus tau, phi prime minus tau into d phi prime into d tau. So now if you observe, this and this are in the same form. Only thing is the phi is replaced with phi prime. So that is not a problem since it is the integrating constant, right? Like the integrating variable, sorry. So we can just integrate, replace the phi prime with phi again. So minus infinity infinity, h1 of phi, h2 of t minus tau and phi we can bring, right? Because subtraction or addition is commutative. So, and then we have d phi, d tau. Now you just make the integrals common. X of tau, then we have h1 of phi, then we have h2 of t minus tau minus phi, d phi, d tau. So this is same as the RHS term, right? So LHS is equal to RHS. So the associative property holds true for the convolution integral. So what does this imply? So this implies I have two LTI system with LTI 1 with h1 of t as the impulse response, and let's say LTI 2 with h2 of t as the impulse response, and I send in a signal x of t, right? And whatever output I get, it will be same if I just replace these two systems by a single system, which is a convolution of the impulse responses of the individual systems. Okay, that is the understanding from this property. So now let us see some properties of LTI systems in terms of this convolution integral. So properties of LTI systems. So the first property we'll see is memory or memoryless. So what did we define memoryless as? Y of t should only depend on x of t and not on its time shifted versions. So in terms of the impulse response, what it means? Impulse response. So it means h of t should be 0 for all t not equal to 0, right? Because only delta of t should be present, should give an output y of t. And any other time instance. So this delta of t, when I say this x of 0 into delta of t, and x of like k delta or tau into delta of t minus tau should not give any, should actually give a 0 output. So that is what it means. So in that case, this h of t itself will be a impulse, and it can be any scaled impulse, right? Scaled impulse. So what are the only outputs? Only memoryless outputs are y of t is equal to k x of t, because it is like x of t convolved with k delta of t, right? Which is nothing but kx of t. So this actually comes from x of t is nothing but x of t convolved with delta of t. And at this point, I think it is important to also see what happens when we convolve x of t with delta of t minus t naught for some t naught. So let us write out the integral. So this is nothing but minus infinity to infinity x of tau delta of t minus t naught minus tau d tau. So we can also write it as otherwise, right? Like delta of t minus t naught convolved with x of t. So this is minus infinity to infinity delta of tau minus t naught x of t minus tau d tau. But this one you know, right? This is only valid when tau is equal to t naught. So you will get x of t minus t naught. So when you convolve x of t with shifted impulse response, you get a shifted version of x of t, time shifted version of x of t. So this is an important result to keep in mind. So next we'll see the invertible property. So we saw memoryless, invertible property. So what does the invertible property says? So if you pass x of t to some signal system 1, so system 1, then you pass it through an invertible system. Yeah. Then you should again obtain x of t. If such system exists, for system 1, then system 1 is invertible. So now in LTI case, what do we have? Let's say the impulse response of system 1 is h1 of t, and then the system 2 is h2 of t, then again I should get x of t. So now what will be this? This actually will be, so what will be this? This one will be x of t convolved with h1 of t. And this will be x of t convolved with h1 of t convolved with h2 of t. So what it means? X of t convolved with h1 of t convolved with h2 of t, right? So this is equal to x of t. But x of t itself is nothing but x of t convolved with delta of t. So this term should be equal to delta of t. So h1 of t convolved with h2 of t should be equal to delta of t. If such h2 of t exists, for h1 of t, then the system with impulse response h1 of t is invertible. Okay, fair enough, right? So as an example, if let's say h1 of t is delta of t minus tau, so do you think such h2 of t exists? Yes, it exists. So let h2 of t be delta of t plus tau, t plus t naught, right? So it is basically right shifting. h1 of t is right shifting by t naught and h2 of t is left shifting by t naught. So they should both cancel out each other and we should get delta of t. So h of t equal to h1 of t convolved with h2 of t is delta of t, which implies h1 of t is invertible with inverse system h2 of t, and vice versa. h2 of t also is invertible within inverse system h1 of t because of the commutative property, right? So next is the causal property. Causal system. So for an LTI, so in general, what is the case? In general, y of t should not depend on the future instances of x of t, right? And in LTI, what do we say actually? So in LTI, in terms of impulse response, we know x of t is like sum or integral, right? Sum of shifted impulses, right? So, and we define output y of t as integral minus infinity to infinity x of tau h of t minus tau d tau. So this tau actually, so x of tau, right? So this tau for a particular t, so if this tau is greater than that t, then this should be equal to 0, right? So y of t should be 0. So which means this integral is valid only from minus infinity to t x of tau h of t minus tau d tau. And who is actually defining this condition? This condition is being defined by this impulse response. So what do we have? H of t minus tau is equal to 0 for tau greater than t. But if we want to write in terms of t itself, so this is for t minus tau less than 0, right? So h of, I'll replace it with some constant phi, is 0 for phi less than 0, or I can replace it with t itself. So this is 0 for t less than 0. So if this is the case, if h of t is equal to 0 for t less than 0, then we can say the LTI system is causal. So it is very nice, right? With just the impulse response, we can actually derive every other properties of the system, given that it is an LTI system, right? So to once again go through, so this x of tau, so this y of t should not depend on x of tau or x of t for tau greater than t, right? For any value of tau greater than t, it should not depend. So what you do, you just put h of t minus tau to 0 for this condition. Then it will not depend. So then what do you finally arrive at is, you arrive at h of t is actually 0 for t less than 0. Okay, so this is the condition for causality. And then the last property we see is stability. So in stability, what do we have? This fourth one, right? Right. So in stability, what do we have? Bounded input gives bounded output, which is also called as BIBO. So we know y of t is nothing but integral minus infinity to infinity x of tau h of t minus tau d tau for LTI system. Then what do we have? We say the input is bounded. X of t is less than some b, or less than or equal to some b. Then we try to find if the output is bounded. So this is nothing but modulus of minus infinity to infinity x of tau h of t minus tau d tau. And you know this is less than or equal to integral minus infinity to infinity x of tau h of t minus tau. So this is h of t minus tau d tau. And you already know x of tau is bounded by b, and b is a constant. So you can take it out. This less than equal to symbol I'll keep it for y of t. So then you have b integral minus infinity to infinity mod of h of t minus tau d tau. So for y of t to be bounded, this integral should be less than infinity. Integral h of t minus tau d tau should be less than infinity, right? So now I can just try to bring it in a good form. So I'll replace t minus tau with phi. So minus d tau is equal to minus d phi. And the limits will exchange, correct? So when tau equal to minus infinity, phi equal to infinity. When tau equal to infinity, phi equal to minus infinity. So this is from infinity to minus infinity, h of phi into minus d phi. So this should be less than infinity. And this minus n I can use it to interchange the integrals. So minus infinity infinity, h of phi d phi less than infinity. Now phi is just a integrating variable. So I can change it to dt. So h of t dt less than infinity. So this is just but the absolute integral. Absolute integral of h of t. And it should be finite. So then we can say, then the LTI system is stable. So this is also called absolutely integrable. Absolutely integrable. So this property is called as absolutely integral. So you can actually see the appreciate results we actually obtained in each one of these system properties, right? So just the impulse response is sufficient to describe the entire LTI system, right? So the impulse response of an LTI system is sufficient to fully represent the system. So, and this is only true if the system is linear and time invariant. Both the properties should hold true, because we already saw in the derivation that we use both the properties, right? So that's it for today. Please go back and revise these concepts once again. See you. Take care.